So we're going to talk today about inertia mismatch. Normally when I tune a system up and I have a nice 1-to-1 inertia matching ratio, it tunes up nicely. A 1 to 10 is not bad. A 1 to 100 is awful. So here I've got a Parker motor with a Copley AEZ all wired up with a large inertia mismatch. It's like 100 to 1, and you can see, we need some tuning here, but there's a characteristic frequency. If I wind it up and let go, it'll bounce. So just some basic ideas. Current produces torque. Directly coupling is the motor inertia plus the load inertia is the total inertia. But a gear ratio can reduce the reflected inertia by a square law. So we can see the motor inertia equals the load inertia divided by some gear ratio squared. So we can calculate the square root of the load over the motor to get the ratio of turns for the gear to make it inertia matching. And again, a 10 to 1 for load to inertia is okay. There's also a energy matching or energy transfer. It's like a couple of transformers that are impedance matched. It's like if you're not matched with inertia, it's like having a sumo wrestler fighting a guy who's got a pair of sneakers. He can run around real fast, but it's hard to deal with the mass of the sumo wrestler. Anyways, to calculate the inertia, we accelerate the we accelerate by applying torque. If we know the acceleration and the torque, then we can calculate the inertia. So that's how I got to measure the 100 to 1. I just did a measurement. But basically, we can see the torque over time is the current over time. The square root of the excelling, running, and decelling current, you should make sure this is always less than your continuous current. You got voltage gives you speed. There's a bunch of formulas for motor modeling. Just sort of a design rule is give yourself some margin. Make sure your RMS current over time is less than the motor's. Make sure you got some DC bus, like use up 80% if you want, but leave yourself some headroom. Check to make sure you're not voltage limited constantly. A little bump your head's fine. Watch the following error. Check the settling time. But back to the inertia thing. Again, I have like a disc with a spring, and I wind it up and I let go and it bounces. Same thing as this old mechanical system is with the new inertia matching. I have a motor inertia. If you hold the shaft and turn the load and let go, you'll see a bounce. That's defined by the torsional stiffness, and there's a damping ratio. So there's a frequency at which it will settle out. And the same thing is true here for the electromechanical time constant. I'm trying to hold the motor shaft. I'm pulling back on the load. I'm letting go. And it responds at the electromechanical frequency. So in a system, we use the loops to control the velocity and position. And what you'll notice is the velocity stiffness, a higher VP, has a higher frequency versus a lower VP that has a lower frequency. So the frequency is dependent on the stiffness of the velocity loop. And the proportional gain, this is a high PP, will multiply the frequency. So this is the amplitude. So a lower PP will give us a nice settling. If it's a 100 to 1 inertia mismatch, that'll have to turn down some more. So we show here the basic kind of 1 to 1, and then 1 to very big. And so the frequency changes. And again, the velocity stiffness is important, but so is the proportional gain of the position loop. If you don't want it to bounce, then you got to turn the PP term down. So if you have a system with resonance, you look at what frequency it is. High frequencies close to the current loop or the torsional resonance. Mediums are like mechanical structures. 120 hertz is interesting because that's rectified line, and so is 60 hertz. But low frequencies and tens of hertz, it could be like the electromechanical system. It could be a large mass that's bouncing. The other thing that's interesting is near zero, you can see there's some crossover distortion when you go from dynamic friction to static friction. There'll be a little crossover there. It's called deadband and backlash, and when you're starting to move, you get some stick slip, and you get some hysteresis and hunting. You know, I'm trying to move. My integrator's winding up. I bounce forward a little bit. Oh, I need to come back. The integrator winds up, bounces back. So a lot of times we'll set the integral to 0 to hold a steady state position. But that's just the basic of the electromechanical system. So we're going to look at some data for this motor. And originally we put in the inertia of the motor, 0.05 kilograms centimeter squared. That used to say inertia because you could put the load in there too, and it calculates initial values. But the gains come up a little high when you have, you know, a large inertia, and there's a coupling. So we have to watch the filter frequency. We'll get to that in a moment here. There's a velocity filter frequency that we will adjust for the large inertia mismatch. But I have a current loop based on the math model. I just need to make sure I have sufficient bandwidth. I like a kilohertz, but 400 hertz is good for today. We can tune the current loop later. So just to skip right into how do I tune for large inertia mismatch? We got our basic current loop tuning. So we have commanded and actual. I use auto setup and hit start. So that looks pretty good for what we're doing here. I'm going to look at the velocity loop based on the math model. I'm going to turn some frequencies down, slow the speed down, turn the XL down. I should probably lower it more, but this should give us something to look at here. So it needs some gain, okay? So I'm going to double the gain here until I break into oscillations, and we'll start seeing some motion here. There we go. Now the gain's too high normally, but with a large inertia, what we need to do is change the pole. Still gives us a high frequency. I'm going to pull it in. So keep pulling it now. We're coming stable again. So I think we can go all the way down to like 25 hertz. I haven't gone any further lower than that, but it's only 100-to-1 mismatch ratio. And this is looking pretty good. There's a point at which it will break into oscillations again. There. So wherever that oscillation is, cut it in half, make sure it's stable. You got some gain margin, now you got some phase margin. If we look at the integrator, if the integral is too high, you get some integral wind up. So there's the overshoot right there. It goes to steady state, so I'm going to knock that back down. So again, the frequency of the response is based on the stiffness of the velocity loop, and we pulled the pole in to 25 hertz. So that's pretty good. I'm somewhere in the range here. Now I'm going to do a little move in position mode. So again, the frequency is based on the stiffness of the velocity loop, and the amplitude is the proportional gain. So knock that puppy down there, make the move again, and we should get a much better responding system. So that's pretty good. I got some following error growing here, but I think my speeds are a little high for the 48 volts I have here. So I'm just going to turn that down. Make sure, make sure you have voltage margin. And so there's sort of a characteristic move here. My XLs and decels may be a little fast for what I hope to accomplish. So we'll make a little further move. Here's a single rev. That was nice. Let's go a little bit further and see if I can go a little bit faster. That was 2 revs. So move and stop. We'll see how that behaves. That's pretty good. Let's do 10 revs. I got 4,000 counts per rev times 10. My acceleration seemed to be a little high, so I'm just going to knock it down again. It's a big inertia. Wow. I think I'm hitting a speed thing here. Let's see if we can slow that down a little bit. Ah, there we go. All right. So we'll do some finer tuning on this. It's as stiff as we can get it without overdoing the resonance here, I think. No integral wind up. We'll try a little bit of a bounce here. Yeah, have to bolt this thing down a little better. But that looks pretty good. I think we have some nice move times and settling. Once you get the system tuned up, save it to flash, save it to disk. I've got a file here that I did earlier. So AEV Parker. Save that to flash. Let's make this move again. No, all right. Yeah, so a little bit more proportional, a little bit higher PP term. And again, this was the important lesson here was the velocity loop pole. Never have more bandwidth than you need. The default's 200 Hertz 2-pole. As we increase the velocity loop stiffness, there's a electromechanical time constant, which brings us down. So might as well pull the pole in at the output of the velocity loop and give us some nice stability in the velocity loop, allow us to increase the gain for stiffness, and we get some pretty good stiffness and good position holding. You know, that'll go, there's some integrator there, so that'll go right to plus or minus a count, and that's some pretty nice. It's a pretty nice move and settle. There's a little ring there. That's okay. A little overshoot won't hurt anything. I'm going here for stiffness and a good step response. Maybe let's not go so far. Let's do a single rev here. Reading trace data from amplifier. There it goes. Yeah, move and settle. You can see the position is dead nuts, 0. There's a little going to steady state, and then a little plus or minus a count thing as the bench stops shaking. It gets to 0 eventually. So my settling time is pretty quick. A nice. The frequency again is based on the velocity loop stiffness, the electromechanical time constant, and the amplitude is the proportional gain. So we're far away from oscillation. If the gain, you know, we double it and double it, we might get oscillations. Always cut it in half. Give yourself some gain margin. Integral, no integral wind up. Keeps it nice and low. Large inertia is usually a small integral. No need to worry about the feed forward term. That's just the error while it's moving. 16384 is the default. But I thought, hey, it's okay. Let's try to come in for a smoother landing. We'll just allow the error to build and then settle it out after the move. And again, the frequency of the velocity loop, single pole, low pass filter, 20 Hertz, right at the output of the velocity loop. That's the best way to handle a large inertia. So thanks for watching.